I think we should start. So good afternoon, everybody. Today is my great pleasure to have Dr. Nathan Grieve from NTU Laboratory, Carleton University, UQAM, and the University of Waterloo. And he will share with us his recent, I think, ideas about the Newton-Okounkov convex bodies, and even talk about applications, classification, and approximation. I think he will give us 4 talks, so essentially. So that's what I'm here.
Okay, so thanks for the invitation. It's very nice to be here. So what I want to do today is sort of explain some ideas in algebraic geometry, and in particular applications of Newton-Okounkov bodies. But I want to sort of mostly, in some sense, focus on sort of what is, algebraic geometry. So I understand there's lots of people here that work in maybe differential geometry and topology, and so I want to try to sort of provide context and motivation for what we actually think about in terms of projective algebraic geometry, in terms of techniques and sort of key guiding problems, and then sort of along the way introduce this idea of Newton-Okounkov bodies, which has been a very significant advancement in the theory in the last 10, 15, 20 years. And then try to give some ideas about applications. So today I'm not going to really say very much at all about sort of the applications to sort of Diophantine approximation and stability. However, I will talk a little bit about some very recent results that pertain to a new construction of Okounkov bodies for what are called divisors on the Zariski-Riemann spaces. So the sort of selected recent related work, so this is just sort of a sampling of some recent outputs on related themes. As I said, I won't get into very much details on most of this. I'll say a little bit of the intent later in the talk to say something about these most recent results. But certainly everything I talk about today is all sort of very relevant to this very exciting story. Okay. So first of all, just some general sort of context. So geometry, topology, algebra, and number theory. So a key goal in all of these fields, we want to classify, again, geometric shapes and structural properties of numbers up to suitable notions of similarity. And so for example, if we're thinking, sort of topologically, we might want to sort of classify topological spaces up to sort of some form of continuous deformation. For example, homotopy. So an issue that arises, while this might be a very sort of useful initial classification tool, we might be sort of missing a lot of refined features. Okay, and so that's sort of the key kind of question you should have in the background is sort of what kind of equivalence relation do we want to sort of do classification up to. So in terms of projective algebraic geometry, so there's many different points of departure, and so I'll try to sort of give you some impressions for a couple. One sort of way I sort of think about projective geometry is that it's somehow comparably more rigid in terms of other kinds of geometries. Especially, if we compare, say, even within, say, Kähler manifolds, but also differential manifolds or triangulated topological spaces. So I'll explain a little bit more what I mean by that, but in essence, sort of this idea of even if I have an even dimensional real manifold and I have a complex structure, that's sort of rigidifies quite a bit, and then sort of one step further sort of is, can I sort of solve the Hodge-Riemann bilinear relations, which sort of turns a Kähler manifold into a projective manifold, and then makes sort of the geometry very algebraic. And so that's very important and very useful, and opens up a whole different sort of kinds of flavor of techniques. So for today, it's fine to think about working over the complex numbers. In practice, many interesting questions start to arise when we sort of think about subfields of the complex numbers. For example, a number field or Q bar, etc. But for today, at least, there's no problem in thinking about sort of the complex numbers as their base field definition. Okay. So first concept. So a very important starting point for algebraic and arithmetic geometry is the study of projective algebraic curves. And so here already, sort of what do we mean by an algebraic curve sort of already arises. So starting maybe from topology, if we think about genus G compact Riemann surfaces, okay, so these are real two-dimensional manifolds, and they have G handles. And so the genus, that's the number of handles, so this is a topological invariant, right, and sort of provides an abstraction from say, making a torus into a sphere, or a genus 2 curve into a genus 1 curve, so on and so forth. So it does capture something, right? But then on the other hand, you know, if we sort of fix the number of handles, there's a whole bunch of different shapes of a particular genus G Riemann surface, and we would like to be able to sort of, you know, maybe tell some more refined features from one to the other, right? So already in the case of genus 1, once we fix a complex structure, right, this is the theory of elliptic curves, and so things become very, very, very rich. So this, you know, example, I think already highlights the difference between, say, if we just want to think about, say, topologically or even differential geometrically, once we fix a complex structure and sort of translate the problem, if you will, into the realm of projective algebraic geometry, we have a whole wider range of refined invariants, which becomes very, very, very rich. So the ambient sort of space to do projective geometry, okay, so this is projective n space. And so there's already, again, a few different ways about thinking about projective space, but for now, let's just sort of think about, we're going to look at, you know, n plus 1 tuples of complex numbers, not all 0. And then we have the equivalence relation where we identify such tuples if their coordinates are scalar multiples of each other. And so projective n space, it's covered by affine spaces. So we have the standard affine open covers. So we cover projective space in this way. We have this identification of each of these open subsets. Ui, so this is where the xi coordinate is not 0, so this is isomorphic to affine n space. And then we have the gluing data. So, you know, if I have on the intersection ui, uj, so this is where xi and xj, these are both not 0, so we have these transition maps. And so it's by this identification that we glue together these open subsets to make projective n space. Okay. So now if we want to think about, well, projective varieties. Okay, so maybe a question that you should have in the back of your mind is these genus G Riemann surfaces that I mentioned before. What do we mean by projective coordinates? And so, I mean, concretely here, if we think about a projective variety as living inside of some projective space, so these are irreducible and reduced Zariski closed subsets that are determined by vanishing of a collection of homogeneous polynomials, and we want that the homogeneous ideal generated by those polynomials, that this is what's called a homogeneous prime ideal. So this is what we mean by a projective variety. More generally, we can consider what we call Zariski closed subsets. And so these are subsets of projective space that are defined by the vanishing of a simultaneous collection of homogeneous polynomials. And so the point here is that the ideal generated by these polynomials, they might not be prime. But these are the basic building blocks. They're closed subsets for what we call the Zariski topology. So the Zariski topology, it has the property that the open subsets are very, very large, and the closed subsets are what we can see, right? So these are sort of solutions of polynomial equations. And so this is the sort of language by which we do projective algebraic geometry. Okay, so it's a very sort of algebraic sort of flavor, and the point is that it really, as I sort of said, rigidifies in some sense the geometry, even when we have an even dimensional real differential manifold that has an ample line bundle after we've fixed the complex structure. so just before we sort of maybe talk a little bit more about that, what are some concrete sort of examples? So here, the rational normal curve. So you should think about this as being this sort of twisted cubic or circular helix that you see in your calculus course. So here we have three global homogeneous equations. So this curve, it turns out to be isomorphic to the image of P1 in P3 by the map that sends these coordinates st to s cubed s squared times t s t squared t3. So this is called the twisted cubic sort of rational normal curve embedding. So globally we have homogeneous equations. So if you think of sort of looking here that you can see, you can just sort of check that each point of this form, it vanishes simultaneously at each of these three polynomials. And conversely, if I have a point of projective space that vanishes at each of these three polynomials, then I can realize it as in the image of this map. Okay, so that's sort of the first kind of calculation to try. Now, one thing that's interesting already in this example is this question about sort of global homogeneous defining equations compared to local affine local defining equations. And so if we look at, for example, the standard affine open subset U3, this would be where sort of the x3 coordinate is not equal to 0. We can sort of dehomogenize these coordinates, and we can look at, well, the image of this curve intersecting U3. Turns out that it's cut out by two equations locally. But however, globally, we need three. And part of the reason is that if I looked in, say, one of these other subsets, U1 and U2, I would get sort of two equations. They would be different, right? But we sort of globally need sort of all three. Okay, so this is a really important subtle feature that causes a lot of sort of, I mean, difficulty is the wrong word, but it's sort of really at the core about what makes projective algebraic geometry sort of important, subtle, and difficult is this sort of question about sort of global homogeneous coordinates compared to what we can sort of see affine sort of locally, and is really sort of at the crux of everything. Okay, so that's a really important sort of point to emphasize. I'm emphasizing today for this very reason. Okay.
So, Mason, so
yes.
Here we see rational normal curve. Then what is the irrational normal curve?
Well, okay, so the rational, so I'll talk a little bit about what we mean sort of by birational equivalence, but quite literally here, I mean, I have a curve that's isomorphic as a projective variety to the projective line. And so that's why I'm sort of calling it a rational curve in particular. The rational normal curve, I mean, is just sort of a terminology that we sort of use because it's sort of for a given d, this is embedded by the complete linear series of degree d with target space P3. And so that's a little bit of specialized jargon, if you will. But the rational part, if you will, this comes from the fact that this is actually the projective line. Okay? So a question that maybe, how do you sort of make interesting subvarieties of projective space? If we just go back to sort of this previous slide here, where I just need to choose a collection of polynomial equations, and that's going to describe for me a Zariski closed subset. But can I say really anything more about that? And so sort of what's going on here is that I'm looking at the map of, say, the projective line into projective 3 space, and I'm getting an interesting collection of equations that's relevant to the geometry of P1. And so that's another sort of point that I want to sort of highlight a little bit later on is this question about, say, projective coordinates, projective realizations of projective varieties in an ambient projective space. That's, again, also at sort of the core of the theory. It's how we extract these classification invariants, arithmetic invariants, as a function of the embedding. Okay, so that's sort of, those are some things to keep in mind here. Okay, so going back a little bit to these compact Riemann surfaces that I mentioned previously, if we look at a degree D plane curve, okay, so here we're going to look at the geometry of solutions of a polynomial in 3 variables of a particular degree. Now it turns out that, again, sort of for general such forms, what we get is a compact Riemann surface of genus G, where G is 1/2 d minus 1, d minus 2. Now, so part of the point here, again, this is sort of slightly not obvious, but true, is that, again, sort of a general such Riemann surface from a few slides ago of a particular G can be sort of transformed in this way, entirely encoded as a solution of such a polynomial. And on the other hand, not all such curves can be done in that way, so there's some obstructions. And so what we can do is we can sort of look at sort of the moduli space of such degree D plane curves. And this is another sort of common feature that we do in projective geometry. The idea is that we can sort of shift focus. We can look at the coefficients in front of these equations. We can look at the projective space of coefficients as being sort of the parameter space of such plane curves. And we can look at, say, a random polynomial or a random point of that projective space. That's going to define, again, a smooth curve of genus G, complex dimension 1, and sort of, you know, in a precise way, but also in an analogous way. We can think about moduli spaces as sort of the sample space of a population, and we want to sort of probe the sample space to see what kinds of geometries that we can encounter. And it's important and interesting to sort of point out that just like in the case of, you know, sort of descriptive statistics, what we can sort of see is not necessarily what's sort of so-called random from the point of view of the sample space, if you will, right? So this is sort of a very sort of important problem in algebraic geometry, this question about, can I actually write down the sort of so-called general object, or are we only really able to sort of capture sort of very special instances, Zariski closed subsets of the moduli space? And so that's also another sort of very foundational problem at the core of the field, which I'll get into a little bit more. Okay, any questions so far? So now I want to say a little bit about some of the more nitty-gritty details about what we actually study in terms of projective varieties. Okay, so the idea is we want to study a projective variety by certain classes of functions on it. Okay, so it's sort of the function theory of the projective variety that allows us to, for example, give projective realizations, and then also again sort of probe properties of its points, the solutions of the polynomial equations that define it with respect to some projective embedding. Okay, so there's this idea of regular functions. So basically, we want to look at Zariski open subsets, and we want to look at functions on this Zariski open subset that can be locally written by polynomials, homogeneous polynomials of the same degree. Okay, so this is how we get functions on the projective variety. And again, sort of the domain of such functions, right, are a given sort of Zariski open subset. And so sort of a very important sort of development in the theory of geometry is this language of sheaves. And part of what that language does is it lets us, you know, sort of keep track sort of all at once these various sort of open subsets. So we want to sort of look at functions as a subset of open subsets, and they assemble together to call what the sort of sheaf of regular functions. And so on the one hand, right, so if I have sort of two open subsets, it's clear that I can sort of restrict domains. The more sort of harder problem and sort of the role of cohomology is sort of to go the other direction. So the sheaf theory seeks to solve the question about, can I patch together functions that I agree locally to make a globally defined function? And that's really the core, the sort of core question about sort of projective embeddings and classification theory and everything like that. So sort of this pair X omega, XOX is a locally ring space in the sense of Grothendieck. The point here is what we call the stocks of function. These are all local rings. Okay, so the sort of the stock is that we just sort of want to look for a particular point. We want to look at sort of all open neighborhoods of that point, and we want to sort of look at all of the sort of functions that are sort of defined there. Okay, so that's what we mean by a locally ringed space. We have again the sheaf of regular functions on X. And then the other kind of very important object, in some sense more classical, is what we call the function field of X. And so the function field of X is sort of surprisingly, in some sense, difficult to think about. But basically all what we want to do is we sort of want to sort of keep track of, again, sort of all regular functions, but we have an equivalence relation. So we basically want to invert, we want to be able to sort of invert functions because we want to sort of be able to, we want to make a field of fractions of the structure sheaf. And sort of the only sort of, in some sense, issue is that the structure sheaf is sort of not a ring per se because it's sort of it's a ring for each open subset. And so what we want to do is be able to just sort of make the field of fractions. So that's what we do. We have sort of this the field, the function field. So it consists, again, of equivalence classes of pairs UF, where U is a non-open, Zariski open subset. And again, we have an equivalence relation if we have functions that agree on intersecting open subsets. And so this is a field, and elements of this field are called rational functions on X. And so the field is finally generated over C. And the algebraic dimension of X is defined to be its transcendence degree. So, I mean, on the one hand, we could sort of take our point of departure for algebraic geometry as saying, let's look at finally generated extension fields of complex numbers. And in that sense, that's the starting point of birational geometry. And then the question is, we want to sort of find models of that function field. In terms of dimension, so this, again, sort of algebraic dimension, so again, it's sort of slightly confusing at first. I mean, even if you just think about these compact Riemann surfaces as being two-dimensional real manifolds, but we think about them as one-dimensional complex manifolds. And so one way to sort of think about that is in terms of the transcendence degree of the function field over C. As just sort of a general guiding principle, if we have an actual, variety in projective space, and we want to say, can I determine its dimension from its defining equations? The answer is, well, sort of that's a little bit more subtle. I mean, at least if you sort of have sufficiently sort of general homogeneous equations, much like when we look at linear algebra and we say, what's the dimension of the solution space? So if there's not, so if the defining equations are sort of suitably linearly independent, then we can just sort of revive. Okay, but that's sort of a general sort of important guiding principle that enters. Okay. So birational equivalence. So now we can enter into this sort of concept of a birational equivalence. So projective varieties X and X prime, they're defined to be birationally equivalent if they have isomorphic function fields. And so within classification theory for projective variety, the main very difficult guiding question is to classify projective varieties up to birational equivalence. And so from the sort of most algebraic viewpoint of non-singular projective algebraic curves, this is sort of going back to insights of Zariski, is that the sort of curve is entirely determined by its function field in dimension 1. So this is sort of, I mean, again, sort of a completely algebraic sort of interpretation in some sense about these, G Riemann surfaces that I drew before. And again, it's a certain amount of work to sort of make precise the correspondence between those different viewpoints. If we want to look at higher dimensions, so higher dimensional, say, finitely generated extensions of C, the situation is much more complicated. And so really, sort of the minimal model program of Mori is sort of one approach to sort of do the classification. So already, again, in sort of dimension 2, we need to sort of start to formulate sort of an idea about what we mean by sort of a minimal model as being, for example, a preferred non-singular model of a given function field. But so there's just a lot more sort of subtleties that arise, and that's just sort of what happens when we start to look at higher dimensions. But sort of as a starting point, what we sort of want to think about maybe is again sort of what we call divisorial evaluations of the function field as being sort of the sort of generalization, if you will, about what we have in dimension 1. And so making sort of progress towards that viewpoint is part of what I want to talk about a little bit today. This idea of the Zariski Riemann space. Okay, but before we get to that, let's go back a little bit more to this sort of question about, again, embeddings of projective varieties. Okay, so I want to try to explain to you this idea of Cartier divisor and line bundle, which again is very much sort of at the core of, say, function field and projective varieties, which ultimately is the sort of foundations for everything that sort of follows. So pictorially, again, just think about here the case of a degree 4 plane curve, okay? And I'm going to cut that curve with a line, and so I get 4 points. So this what this picture is saying is that I have a non-hyperelliptic genus 3 curve in its canonical embedding. So I have one of these Riemann surfaces with 3 handles, a sufficiently general one of them, and I can realize it as a degree plane curve of degree 4. And so it turns out that the points of intersection here with this general line, this gives a divisor. It determines what we call a Cartier divisor on the curve, and that data also determines a line bundle. And it turns out that data, in essence, is entirely responsible for that projective realization of that curve. But there's sort of also some other sort of subtleties in the background, which I won't get into too much, but this idea of what we call linear equivalence. So the idea is, for example, I could say fix one point and I could sort of move the line around, and I get sort of a whole bunch of other sort of points where I could also just sort of choose another line and intersect, and I get a bunch of other sort of collections of points. So there should be something special about the configurations of points on the curve that we get by intersecting with the line. And that answer is yes, that's true. And that's something that we want to sort of capture, for example, by this question of linear equivalence. And also, it turns out, by this question about global sections of line bundles, which is something I'm also going to get into a little bit more detail. Okay? The key point to remember is that for a given projective variety, every very ample line bundle, something I'll say a few words about in a minute, but every very ample line bundle with n+1 dimensional space of global sections determines a collection of projective coordinates on the projective variety. And that's what we want to sort of study, is sort of embeddings as a function of projective coordinates, and as a way to, for example, understand the classification problem. Okay. So now I'm going to try to, so this is the sort of this idea of Cartier divisor, okay? So this becomes a little bit more technical, but hopefully not sort of too bad, as we have some prerequisites. So the idea is that we want to fix a Zariski open cover of the projective variety together with a collection of rational functions, and then we have this condition that on the overlaps, these ratios Fij, they're going to be invertible regular functions. And so the point is that so such data determines what we call a Cartier divisor. And now the Cartier divisor determines what we call a rank 1 locally free submodule of the field of rational functions. And this is what we call the sort of line bundle associated to the Cartier divisor. Okay? So there's a map, D to OD, and this gives a bijective correspondence between the collection of Cartier divisors on X and the collection of line bundles, that is the collection of locally free rank 01 submodules of the field of rational functions. So this is a little bit sort of more technical algebraic sort of viewpoint. I mean, I have to sort of explain to you, sort of, you're familiar with sort of the theory of modules over a ring, so then there's a theory of modules over sheaves of rings, sort of so-called sheaves of modules. But in the simplest sense, this is what we mean, and almost in the most geometric sense, this is what we mean by sort of the data of Cartier divisor. And sort of there, you could ask sort of about the question about sort of the isomorphism class of this line bundle and how this compares to, for example, what we call the linear equivalence class of this Cartier divisor. And that sort of has to do with, in some sense, the freedom of choices that we have for functions defining sort of the same Cartier divisor in a way that can be made sort of precise. So that's a little bit more complicated, but actually, as I sort of explained sort of previously, this idea about let's choose a different line and intersect the curve and look at the points that we get, those two problems turn out to be very related. Okay. Okay, so in a nutshell, this is what we mean by Cartier divisor. Now, global sections of Cartier divisors. So in essence, these are what are responsible for projective coordinates on the projective variety. And so I'm wanting to sort of again try to explain this to you, to sort of highlight again sort of how we use projective algebraic geometry techniques to study and to answer this question about projective coordinates. So there's a patching condition. So the point is that we look at the ratios of these two functions, f, I, j, that are defining data for the Cartier divisor, and we get these transition functions. And so global sections, we want to look at functions that satisfy the patching condition. So as I said, sort of in this language of sheaves, if we restrict domain, we can always get functions. The more complicated questions come backwards. And for the case of these Cartier divisors, that's exactly what's happening, is that we have, again, sort of patching conditions specified by these transition functions, which are determined by the local data of the Cartier divisor. And sort of the Riemann-Roch problem, it asks, can I determine the nature of the function? M goes to the dimension of space of global sections of the M times D, where M times D is the Cartier divisor that's determined by the powers of the defining equation. So this is sort of the M-fold tensor product of the line bundle. Okay, so this is again a very classical problem that can be formulated in the language of commutative algebra in a very important way. And part of what I want to try to explain in the rest of the talk is about sort of how this remarkable theory of Newton-Okounkov bodies somehow basically sort of answers the Riemann-Roch problem. And that's a really important advancement in the theory. So let's first maybe just look at a few more examples here. So again, if I look generalizing the case of a degree D plane curve, I can look at a degree D hypersurface in Pn. So this is going to be the vanishing of a degree D homogeneous polynomial. Now, so this determines a Cartier divisor on projective n space. So I should also say there's sort of a theory of V divisors for normal projective varieties that's closely related to sort of Cartier divisors. And in some sense, the singularities of the varieties is sort of measured in the failure of V divisors to be Cartier divisors. So that's another sort of important chapter of the theory, if you will. But at the moment, you don't sort of have to worry about that for now. But the reason I sort of mention this is that sort of the zero locus of a single equation in projective space, right, that determines a codimension 1 algebraic subvariety, turns out to also specify a Cartier divisor. And the C vector space can be identified with degree D polynomials in n+1 variables. And so the point is that, well, we can just sort of count, right? We can count the number of degree D monomials in n+1 variables. And then it turns out, calculating the space of global sections by the method that I described for you earlier, we can answer the Riemann-Roch problem in a direct way. Now, for an arbitrary sort of projective variety and a divisor, of course, we can't do these calculations explicitly. And so sort of that's part of the whole sort of theory of say, check homology theory or whatnot, to try to sort of extrapolate to an arbitrary projective variety the calculations that we can really only do for projective space. And that's just sort of the way the theory works. So just again, sort of now this idea about very ample versus ample line bundles. So now I'm getting a little bit more into the sort of nitty-gritty about how we make maps to projective space as a function of the divisor. And so again, this is getting a little bit more into the core of the sort of tools that we use to study projective varieties. So there's this question about sort of base point free linear systems. So you should think about, again, sort of global sections of a line bundle. These are basically sort of functions on the projective variety, and we can ask, do they sort of simultaneously vanish or not? In the case that they don't, then we get what we call a base point free linear system. And so we can ask, the map that we get to projective space, is this an embedding, right? So this map from P1 into P3 that I wrote for you before is an embedding. And so you can imagine settings where we're not going to get an embedding. but you can imagine settings where we can't. And so a line bundle or a Cartier divisor is called very ample if I look at the embedding to projective, or I look at the map into projective space given by the space of global sections, that this is an embedding. And so there's also sort of what we call ample. So ample sort of means that I take some tensor power and I get very ample. And so so this sort of condition turns out to be, I mean, again, it's sort of, in many ways, it's what we can sort of see from sort of point of view of polynomial algebra. So I'll try to sort of make that a little bit more explicit. Again, at a conceptual level, each choice of very ample line bundle determines a collection of projective coordinates. And so what we want to do is sort of study, again, sort of x as a function of its coordinate systems given by sort of ample or very ample line bundles. The problem is that, in some sense, so the sort of study of ample line bundles is of intrinsic interest, but then there's other very important sort of line bundles, for example, what we call the canonical line bundle, that, I mean, might not be ample, and even its sort of the anti-canonical bundle might not be sort of ample, but it sort of sees the sort of harmonic analysis, if you will, of the projective variety, and so we want to sort of capture that kind of information. Okay, so this is just sort of the sort of the starting point for those kinds of questions. So here, this concept of big line bundles. So sort of what maybe I just want to make sure I have enough time here, which I think I'm doing.
I have about 23 minutes.
This is good. Okay, good. So let me just go back a little bit here to this Riemann-Roch problem. Okay. So the understanding of sort of this function, or if you will, maybe say the growth rate of this function is the kind of point that we want to sort of keep in mind. And so when we look at sort of big line bundles, the point here is that you should think about that the growth rate is really sort of as large as possible. Okay. Now the big line bundles, they might be ample, but they might not be ample, and there's really sort of, you know, that's just sort of the way things are. Okay. So there's what's called the ample cone, and then there's what's called the big cone, and then there's a closely related concept of, say, nephness versus suitable effective. And sort of the difference amongst all of these sort of interrelated concepts is, again, sort of at the core of even birational classification theory. So part of one way of thinking about Mori minimal model program is to sort of make closer the big cone to the ample cone in a way that's made sort of precise by certain minimal model programs with scaling. So that's something I'm not going to get into in very much detail at all, but I did want to sort of mention that now. And so this idea about, again, sort of bigness for line bundles is that there's this quantity sort of called volume of a line bundle, which you should just think about as really growth rate of space of global sections. And that growth rate of global sections is sort of large as possible. When I say large as possible, meaning that I mean, sort of polynomial is wrong, but at least sort of asymptotically, it sort of grows, its leading term grows as large as possible in terms of sort of the dimension, okay? So this question about whether is the growth rate actual polynomial or not, that turns out to be really sort of a question about sort of ampleness versus bigness a priori. And sort of what can we say maybe in the case where we don't get sort of growth rate sort of as large as possible? And so that's what we sort of call the Taka dimension of a line bundle. So that's sort of the summary slide here. This is sort of the various sort of basically asymptotic growth of linear series. So these are all sort of the key invariants, if you will, that you should sort of keep in mind. So I mean, on the one hand, we have, again, sort of x an embedded projective variety. There's what's called the Hilbert function of the homogeneous ideal of I and x. And so in fact, I sort of, for better or worse, I decided not to really say too much at all about sort of the homogeneous ideal and the homogeneous coordinate ring of a projective variety. Partly because that's a source of confusion in some sense, but it's also actually very subtle and also sort of very important. And it turns out that, I mean, sort of the Hilbert function of the homogeneous ideal is very much related to sort of the Hilbert polynomial of, say, the polarization O1 that's responsible for the embedding of x and Pn, But then again, that's sort of only sort of true asymptotically in sort of some subtle condition of that sort of saturation, again, which is that sort of the core of what makes projective geometry difficult. So anyways, but so there's what's called Hilbert polynomial of an ample line bundle. And part of what's sort of under the hood, which I'll get into in a little bit more, is there's what's called section ring of a line bundle. And we want to sort of understand the growth rate of that graded algebra. And this is the same quantities that we're actually sort of getting there. Okay. Now, sort of global spaces of sections of line bundles on X. So there's what's called the Euler characteristic. And part of the role of the cohomology theory, which is sort of another important achievement of the more modern algebraic geometry, to understand that there are higher cohomology groups that sort of provide an obstruction for calculating global sections. And so sort of what we can see, for example, by, say, Riemann-Roch theorems, is really sort of estimates for the Euler characteristic. And so part of the role of say, positivity or vanishing theorems is to try to sort of, again, estimate H0 in terms of growth rate of, say, lower or higher dimensional cohomology groups, again, asymptotics. And sort of part of, like, sort of the volume function, for instance, that's what it's sort of trying to capture, sort of the sort of normalized growth rate in terms of the sort of coefficient here if we have sort of the maximal growth condition. And the Ataka dimension, as sort of discovered by Ataka, it's sort of trying to capture the sort of largest growth rate. Okay, so that's sort of that's you know, so we might not get sort of maximal growth rate. And so that's another really important sort of idea of Ataka, that we want to sort of look at the maps of rational maps of a projective variety into projective space as functions of powers of a line bundle. And a very important sort of theorem in that viewpoint is that sort of asymptotically we get sort of birationally equivalent to what we call an algebraic fiber space, in the sense that the dimension of the image of that map stabilizes, and that's what's computed by the Ataka dimension. There's another very important quantity that we call Kadir dimension, and that's a little bit, that's closely, in some sense, closely related to Ataka dimension. It's a little bit more involved to study, but really we sort of want to look at, we take a desingularization, and we want to look at the Ataka dimension of the canonical divisor and desingularization. And sort of the important theorem is that this is birationally equivalent in a simple sense, and generalizations of that idea is again sort of also a very foundational topic in birational geometry. Okay, so again, sort of this is a very sort of important sort of summary slide, and I hope that I've given you some impression for actually sort of what goes on in the background. And so now part of what I want to sort of talk about is sort of how the theory of Newton-Okounkov bodies really gives an answer to sort of this question and sort of and generalizations thereof. So there's this idea of divisorial ring. So this is now getting a little bit more sort of general discussion, but this is sort of the graded algebra that comes out of these Cartier divisors. Okay, so this is a graded ring, and quite generally it might be finally generated and it might not be finally generated, but it's a graded algebra, and we'd like to understand its Hilbert function. Okay, so that's just, again, sort of a classically motivated question. Just understanding the Hilbert function, this is a more refined question of the Riemann-Roch problem for the divisor, because the Riemann-Roch problem is like, can we just asymptotically at least determine, and can we actually sort of calculate it bang on the nose? And that's already a very difficult problem in commutative algebra in general. And sort of part of, again, sort of motivation for such question, right? So if you, one of the very first slides I was claiming to you, again, there's lots of applications to the anti-arithmetic geometry, stability, so on and so forth. All of that is true. but I'm just trying to give you some flavor about what's going on first, just sort of for this question about what are some of the main objects of study before how we apply all of these theories to answer those important questions. And as they said, sort of the theory of Newton-Okounkov bodies is, again, a very important advancement in our understanding about how we can sort of see growth rates of sections. And for example, the differentiability of the volume function for instance, is an important related idea that this theory sees. Okay. So some conceptual comments before we talk about, again, what are these. So in terms of recent progress, so Lazarsfeld and Mustada, they developed the theory of Newton-Okounkov bodies, but then also from a slightly different and in many ways more general point of view, Kave and Kovanovsky developed a parallel theory. And the point is that in terms of the geometric content, we want to understand the asymptotic natures of the Hilbert function. And so if you're sort of familiar with the theory of toric varieties or the Newton polytopes that we sort of talked about, that's part of what's going on, is that we want to somehow encode sort of sections, or at least combinatorial data that asymptotically sees all of those sections. And that's sort of the key insight. And so this theory, it plays a key underlying technical role in the spectacular progress that's been made in terms of K-stability, in particular validated criteria for K-stability of faunal varieties, and then also Diophantine approximation for projective varieties, the interactions amongst these ideas, and many other interesting topics. Okay. So here is an example. So sort of if we look at, say, a plane curve, if I fix a point, so I sort of, part of what's in the background to defining Newton-Okounkov bodies is really, in essence, fixing what we call a system of parameters amongst a non-singular point of a projective variety. So one way to sort of do that is to fix what we mean by sort of an admissible flag of subvarieties. And so for a degree D plane curve, we can actually sort of form a triangle in the plane that encodes spaces of sections of that line number. And so if we calculate this a normalized volume, like the area of this triangle, we see that, again, we get a scalar multiple of the space of the growth rate of space of global sections as determined by the Hilbert function, which we can just sort of calculate by hand in this particular case. And again, if you're sort of familiar with maybe thinking about P2 as a toric variety coming from a fan, and you look at, say, the polytope of a torus, one of the torus invariant divisors, and then you could try to sort of rediscover sort of this realization of that sort of polytope, and that's a very important guiding example. Okay. So one of the sort of key sort of starting points, motivation, is this result of Lazarsfeld and Mustada and Kave-Kovanovsky that for a big divisor on a projective variety, the Newton-Okounkov body has the property that its Euclidean volume, its normalized Euclidean volume, bang on calculates the volume of the divisor. Okay, and part of the work of Kave-Kovanovsky, again, starting from a slightly different viewpoint, but they actually establish a much more general result for arbitrary divisors that similar sort of considerations hold true. The point is that the sort of the dimension of the Okounkov body for an arbitrary divisor is going to be the attacker dimension of the linear system, and then the asymptotic growth rate of the section algebra is equal to the normalized volume. Okay, so there's quite a bit sort of more that goes into sort of that viewpoint. It's sort of, I mean, so they're able to prove a much more sort of general result, but in some sense, some aspects of it is sort of explicit. So again, there's a refinement to all of these sorts of things. There's lots of very interesting sort of happenings, if you will, underneath the hood. And again, sort of another sort of point to keep in mind is that the algebras, these section rings, these don't need to be finally generated anymore. Okay, so that's why these results about growth rates of these Hilbert functions is going sort of beyond what is sort of classically done in terms of Hilbert almost for the case, even just going from the sort of homogeneous order concept of projective varieties. Okay, so now maybe let me just sort of go. Okay, so now I'm sort of getting close to time here. So this is sort of the construction of Newton-Okounkov bodies in the classical case. The idea is that we have an admissible flag of subvarieties. We get some valuation function from which we're going to get a graded semigroup in this closed convex cone, and sort of the slice here determines what we call the Newton-Okounkov body. So this is very similar sort of to the approach of Kaveh-Kovanovsky, but they get a little bit sort of more general mileage by working in a different more general setting. And so it turns out, this is sort of now some of the more recent results, which I want to sort of explain, very sort of exciting results about divisors on the Riemann-Zariski space, or the Zariski-Riemann space. So we want to sort of look at sort of the collection of all sort of models of a projective variety. And once we do that, we can look at what we call sort of birational divisors, sort of birational Bay divisors. So this is a very important sort of chapter in the divisor theory that was discovered sort of by work of Shakurov and independently by Vojta, and ultimately sort of plays, again, an important role of differentiability of the volume function. So there's been recent sort of progress and interest in understanding sort of divisors in this space, interpretation of the volume function in terms of positive intersection products, so on and so forth. And so the point is that we can actually look at what we call sort of a divisorial, birational divisorial section ring. For a given sort of normal variety, there's this concept of B divisor, and there's this divisorial section rings that come along with the ride. And so these again are a new class of graded algebras. They're related sort of to section rings of divisors, or rather the trace of the divisor, the birational divisor on X. But they're different objects. They see sort of the valuations, sort of all valuations with centers on X. And the point is that there exists a theory of Newton-Okounkov bodies for such algebras, and the growth rate of the Hilbert function is also calculated in a way that's done in the classical case. And the reason that one can sort of prove such a result is, again, it's applying the theory of Kaveh-Kovanovsky. So one important aspect to their work is this idea about algebras of almost integral type. So the idea is to view, again, sort of such a ring as a subring of the function field adjoining a single variable to sort of keep track of the gradient. And so the point is that one of the important results that Kaveh-Kovanovsky proved, for example, is that the section ring, the classical section ring of a Cartier divisor is almost an integral type. And it turns out that sort of applying that result, again, there's a little bit of proof involved, but it allows one to sort of deduce for these cases, these divisorial algebras. And then as a consequence, we get that the Hilbert function, again, is calculated by the normalized volume of such function, the dimension, again, sort of an attack dimension, if you will, something that is sort of defined, well defined by the same theory, arises from this. So it's sort of funny how I sort of stumbled upon sort of this problem and also this result, sort of this past sort of, these kind of things have been in the back of my mind for some time, but I had a long delay in an airport traveling to the Summer Research Institute conference this past summer that turned out to be sort of quite useful to sort of think about some setup somehow for this problem. And so anyways, and so studying the work of Kaveh-Kovanovsky turned out to be sort of quite useful. If I have just maybe a few more minutes, just to try to sketch very quickly here some of what happens in the toric case. So understanding what happened in the case of toric invariant B divisors in the toric case turned out to be a very sort of important starting point for this. So sort of already generalizing that picture is how sort of the general result came to be. So in the toric case, so the toric Zariski-Riemann space, so it's slightly different setup because we're just looking at sort of toric models. So really this is all sort of fan theoretic sort of data refinements of the fan. There's a toric Zariski-Riemann space. But the point is that, again, sort of there's the polytope theory for toric divisors that we can convert into the sort of Newton-Okounkov body picture by suitably choosing a torus invariant admissible flag of subvarieties. In essence, is the same thing as choosing this system of parameters. Okay, so that's sort of what's happening. And so the point is that we can look at, we can realize this sort of Riemann rock space, this birational Riemann rock space Again, X here is a non-singular toric variety. But we can give a combinatorial realization of these spaces of global sections that fits well with, again, this classical picture about realizing spaces of global sections, torus invariant sections, as actual lattice polytopes of suitable toric polytopes. And the point is that all sort of fits well, again, with this picture of the toric Newton-Okounkov bodies. So this is sort of the punchline, if you will, that we get the dimension of these. So the Hilbert function, again, in the case of the slide previously, but we get sort of the asymptotic growth rate, including the coefficient of the Hilbert function. And again, the point is that this might not be a polynomial, but still that's what we're encoding. So anyway, so I should probably stop there. But sorry, that's what I wanted to report on.
Thank you, Nathan, for this very deep talk. Okay. So any comments, remarks, suggestions? Maybe just raise your hand and ask. Maybe let me walk up with a question I often ask because I am a mathematician in dimension. So you have a construction, you have an existent result. How about, do you have a uniqueness? The normalized.
So that's a good question. So
normalized stuff. Yes.
So okay. Maybe okay. So that's
can you go back to the main theory?
Let me go back to a couple. There's when you say
for example.
Right. Yeah. Okay. So when we say sort of uniqueness, I mean I should probably go back to
maybe module some symmetry. Normalized.
So I should really sort of the uniqueness question. In some sense, this is maybe the starting point is sort of to go back here. We have to sort of say, so what do we mean sort of by uniqueness? So there's a certain amount of complete non-effectivity in the general case. That's just sort of, you can't sort of, and that's because there's all kinds of other invariants in the background that I'm not sort of telling you about sort of the so-called semi-group of the divisor, sort of where sort of sections start to appear and where they don't appear, things like that, and then with suitable assumptions, you can try to make that sort of more effective or not, and that's also a very important technical question in algebraic geometry. Even already just discussing the differences between the approach of Lazarsfeld-Masada and Kaveh-Kolanowski, also very interesting. Because, again, sort of in some sense, you can think about the Lazarsfeld-Masada theory as maybe being maybe sort of more refined and more explicit at the cost of requiring sort of an admissible flag of subvarieties and saying results about sort of big divisors. And so then you can sort of start to ask questions again about sort of the dependence of this Newton-Okounkov body constructed in that particular way as a function of, say, the admissible flag of subvarieties or the numerical class of the divisor even, so on and so forth. And that's not what's going on in the Kaveh-Kolanowski approach. There, it's sort of, in some sense, less explicit, but then much more general. Because their starting point is basically studying graded semigroups, and so it's just sort of, and it's sort of their sort of relation to the geometry is sort of, by the way, our general theory as an example of it outcomes this sort of construction for the graded section rings that are coming from algebraic geometry, and so that's they're very sort of similar and related, but still inherently different. And again, just sort of in sort of full generality for an arbitrary Cartier divisor D, that's, I mean, there's limits to sort of what you can do. But it's sort of an interesting follow-up question is if we sort of trace back through, can we sort of give a little bit more explicit results, possibly with some more kind of refined, to sort of go back and rework some of the Lazarsfeld-Masada idea for an arbitrary Cartier. Those kinds of things sort of haven't sort of been done. And similarly, even more generally, going into the case of these birational Newton-Okounkov bodies, that's another sort of, I would say, wide open sort of approach. In fact, sort of my original sort of approach to sort of doing this, motivated sort of more by sort of the examples that you can sort of see by the toric geometry was constructing sort of a suitable birational admissible flag of subvarieties, which is a completely sort of valid construction. But then once I studied in more detail the work of Grieve, that sort of didn't, in some sense, needed to sort of get at those key results. But sort of a separate kind of question is anything more refined somehow seen by that other approach? And that's sort of another separate interesting topic for follow-up at that stage. But again, there's going to be the theory. This concept of birational divisor again is very, very general sort of object that's sort of so there's going to be anyway. So what can and sort of basically why limit?
Okay. Thank you. So further questions, comments? Yes, thank you for your
I'm sorry. And in your previous slide, the divisor there is a Q-way divisor or is it R-way divisor?
Oh, so
Is it a R-Cartier divisor?
so the short answer is so an arbitrary QA divisor is sort of fine in sort of full generality. I'm sort of sweeping under the rug sort of how we sort of so in the sort of the proof of I guess whichever one of my theorems that I was mentioning. So part of the proof involves fixing the resolution of the singularities and then sort of relating the sort of trace of the birational divisor to some actual Cartier divisor. And so I should say maybe already just applied to QA divisors, this result is already an improvement of the Quebec-Colonoscopy result.
And when it's not big, when the divisor is not big, how do they normalize the volume?
Well, so that's seen by the attacker dimension of the divisor. That's sort of the I guess that's the dimension. Yeah, so its dimension equals the attacker dimension, and then the normalized volume is equal to sort of the normalized sort of growth rate. But there's sort of, I mean, it's not sort of super sort of explicit in the sense that, again, sort of part of what's going on. Again, there's these semi-group sort of, so the normalized Euclidean volume of the Okounkov body. Again, the dimension of that is the attacker dimension. Well, sort of what do we mean by the attacker dimension of the birational divisor? But sort of its traces. so anyway, so that's the idea. Does that make sense? Excellent.
Okay, thank you. Further questions, comments?
I should say, I mean, even just writing, even just writing down the birational divisorial sort of algebra. So this is sort of already sort of somewhat of a new concept. I mean, it had been written down by others, but sort of asking sort of what do we mean by this to be finitely generated in some sense is also completely not known. And various different approaches and conjectures about algebras related to that might be sort of doing that. And sort of one other sort of starting point to this was some sort of musings about what would it mean for sort of a certain sort of log canonical divisorial algebra of this flavor to sort of be finitely generated as a generalization of an abundance conjecture. And that's still a very sort of interesting question, but yeah, it's quite difficult. So.
Thank you. So further questions? So if this is not the case, then maybe I can make a small remark for you. So at least today, I learned that Newton is not just a pioneer in differential equation, astronomy, classical dynamics, but also algebraic geometry. Okay, you should remember this. Newton is a genius also for algebraic geometry. Okay, so I think we should thank the speaker, Dr. Nissan Grieve again. Thank you.